Okay. Okay, let us start now with our first speaker, Catrina-Hamilton, and she will tell us about the history of KH14D and the status of observations and new interpretations.
Great. Well, thank you so much for inviting me here. I appreciate the opportunity to come here and tell you about the history of KH15D, at least from my perspective. I'm really excited to share with you some of the latest observations that we have in hand, and also tell you about some of the new interpretations that have been considered. So before I lose you, I just wanted to say I'd like to just sort of give you some main takeaways that I want you to get from this talk. The very first one is that what I want you to take away is the fact that KH15D, also known as V582 MON, is really an ordinary binary system. It just happens to be in a very unique position with respect to our line of sight here from the Earth. And we've been utilizing this unique orientation for the last 20 years to learn information about the close stellar environment of the system as well as the properties of the circumbinary ring. Also, as we've seen here at this conference, not only on Monday, but yesterday, there are lots of precessing, non-aligned circumbinary rings and circumstellar rings that are being discovered. And I think that what KH15D does is it presents us with the ability to map the inner structure of the inner portion of the disk. And so what I'm here to stress is that we don't have much longer to use this unique position, and you'll see why at the end. And so my strong message is that we really need to exploit the system as much as we can, because time is short and this is not working anymore. No. The last point was we still have so much to learn. Okay. Yeah, okay, main takeaways. And yes, there's still so much more to learn. And I always like to start with this first slide because this is the history of KH15D after all. And my name is Catrina-Hamilton. And so for a long time, people have always thought that the KH stood for me, and in fact, that's not true, because my name starts with the letter C. But anyway, Bill Herbst actually was at Wesleyan University in the early 90s, had a 0.6 meter telescope that he was using to look for rotation periods in young clusters. And he moved on to looking at 2264, and the interesting thing, if you remember back in the early 90s, the chips were like really small, and so he and his students actually needed 4 different pointings in order to image all of 2264. And so it turns out that this object that we are calling KH15D was actually the 15th star in their D field. So it was like A, B, C, and D. And so that's actually where the K and the H come from. It's Kristen Kearns was the master's student at the time working with Bill. These are our quote-unquote discovery images. You can see that KH15D basically disappears almost entirely. It goes down by 96%, almost 3 magnitudes. And we noticed it had a period of 48 days. In doing my dissertation research, however, I found that we did not actually discover KH15D, as we were calling it, in 1970. And of course, you'll note this is a Russian circular, so I'm sure there are many people in this room who can read this. Badalian and Aristova actually had made an announcement that they had discovered 8 new irregular variables in the young cluster NGC 2264. And of course here, KH15D is noted as number 4, and here it is in our image. So this was noted first in 1970, and then it went into the 58th catalog of variable stars in 1972, and therefore became V582 Mon. These are some of the initial eclipses that we had at Wesleyan, and of course, we found that this was really a strange, not T-Tauri type behavior, because we were looking for rotation periods, and then it became very regular. And what's interesting is if you take these data and you phase them at that 48-day period, this is sort of what I just showed you. And then a few years later, you'll see that this return to maximum brightness had completely gone away. And the other part of it was the eclipse was getting wider. And that was sort of the point where we started getting a lot of people interested and into working on this, because we didn't really know what it was at the time. And there were many ideas that were put forward in terms of large vortices of particles orbiting a single star, and other ideas had been floated. We obtained spectra both in eclipse and out of eclipse, and we did not see any change. This was also found by Eric Agol et al. And so effectively, we started thinking that perhaps this thing that was causing the eclipses was either made of very large grains, or it was an optically thick disk, or maybe some combination of the two. There were some historical studies that were performed. Josh Wynn at the time was at the CFA and had access to the Harvard archive, and found that between 1913 and 1955, he could find that there were no eclipses going on. So, using the current day ephemeris, he would go back and didn't see, if it should have been faint, it wasn't, if it should have been dark, it was bright. So he couldn't find any eclipses. As I said, it was noted as an irregular variable between 63 and 68. And then between 67 and 82, John Johnson and Josh Wynn teamed up, and they went to the Asiago Observatory and looked at a whole bunch of plates there, and actually found that it was going through an eclipse, but the eclipse was 180 degrees out of phase. So where it should have been bright, it was faint. Where it should have been faint, it was bright. And the entire system was brighter by almost a magnitude. So here's this is my international campaign that we had. Peter was working on that with us, and so here is the light curve from 1967 to 1982. Overlain on the 2001 eclipse. So you can see that it was really becoming an even larger puzzle. Maffei et al. Also had blue and infrared plates that went back to 1955, and they also re-examined their plates, and you can see the top panel here is from starting in 55, the last one ends in 1970, and it's really not until the late 1960s that you can start to make out what looks like some sort of a periodic curve. One of the things that we wanted to do early on was we wanted to try and get high-resolution spectra so that we could calculate the radial velocity of the system, or whatever was going on. We were looking for information, what was in the disk, et cetera. And so this graph shows you the plot of the photometry between 2001 and 2006. And all of these dashed lines, which I am not sure that you all can see from where you are, indicate where we were able to obtain spectra, high-resolution spectra. The one that I sort of would like you to focus on is this run that we had right here. This was with the VLT and UVES, and it went over through an ingress. And one of the great things about this is that you can actually use the star and the disk. The disk becomes a natural coronagraph, and the star acts as a probe behind the disk material. And so this is sort of what we were doing. We used all of the spectra that were out of eclipse to calculate radial velocities, and we were able to determine, in fact, that the object was a binary. And the modeling pretty much matched the 48-day photometric period. So that was sort of our slam dunk. We know what it is now. It's a binary system, most likely surrounded by a circumbinary ring. This is the artist's rendition of the orbit. Yep, perfect. It was perfect. It worked during the break. Okay, so anyway, sad, very sad. It's so nice because what you see is the two stars are very eccentric and orbit about a common center of mass. And as they orbit, this ring precesses up across both. I have a less exciting video or picture later. So if you don't quite get the system yet, it's okay. It took us a while. Okay, can we advance it? Is it stuck? Okay, let's see if we can just move right. Oh, nope. Yep, that is not. That's where we were. Okay, so so as I said, one of the things that we can do when we have a star that's setting behind a circumstellar or circumbinary ring is that we can use it. We can use the ring as a coronagraph, and that's what we did. So again, here we're going to focus in on these lines right here and show you how the H alpha profiles change over the course of 5 nights. And what we see here is that these X values are simply telling you how far above the star is from the circumbinary ring. So a negative number means above the ring. If it's 0, it's half covered. If it's positive value, it's below the ring. And so what you see is that as the star sets, the self-absorption in the H alpha line basically goes away. And what's left behind is just this double peak. And so we interpreted that as having evidence of an accretion stream that is associated with the star as it sets down below the binary. We also looked at oxygen 1 profiles because we know that the forbidden emission lines are an important diagnostic of outflows from star. And so we saw that the H alpha line was very interesting. And what we found here, again, this is a pretty busy plot, but this is looking at almost not quite all of our oxygen 1 lines, but these 4 colored ones are plot profiles that were taken outside of eclipse, and we actually subtracted from that a K5 template in order to remove the absorption features. But the takeaway here is that the oxygen 1 line is double peaked and it doesn't really change over time. We assumed a jet speed of 200 kilometers per second. We're able to calculate the inclination angle of the jet to be about 81 degrees. Recently, most recent paper says, wait, there's possibly a different interpretation. Maybe it's not. Maybe this is not evidence of a jet. The interpretation now, as one option, is that the profiles actually arise from a hot surface of a gaseous disk surrounding the binary. And their calculations would say that this hot gas is in a ring about 3 astronomical units in Keplerian motion. We suggested there was an outflow, and we were really happy when Tokunaga et al. Imaged the outflow. Here, this is KH-15D. These images are in the K-band. This is the full shot. This is a blown up one. You can see there's 2 knots. Down here, this is molecular hydrogen, so you can see there's the outflow. The interesting thing to note here is that there's only an outflow visible in the northern direction. There's a hint that maybe there's some nebulosity here towards the south, but we're still not sure if that is actually an artifact or not. This is the continuum image where it does not show up. And the one thing I just want you to do is just keep this in mind as I continue on with my talk. Okay, so here's sort of our summary that we have. It's not inclusive. It's not all inclusive. It's what I could fit on the page. But basically, KH-15D is a member of 2264. It's pre-mean sequence, so it's 3 million years old. It's about 760, 780, I think is what Gaia told us. And the period is 48 days. It's relatively eccentric. The semi-major axis is 1/4 of an AU, and again, the inclination angle. So we're looking at it almost edge-on. In 2004, there were two modeling papers that came out simultaneously that modeled the system as being surrounded by a precessing circumbinary ring that had a very short edge in the front, a half an IU, but it extended out to be about 5 astronomical units. And we could tell by the way that the light curve went that the front edge was very sharp, tidally constrained, but we weren't really sure why it had to be at the width had to be at 5 astronomical units. As I said, there's also evidence for outflow, H-alpha variability, and it's a weak X-ray emitter. Here's the light curve in 2010. So these first few years here, those were the ones I showed you earlier, and then this is kind of what we saw happening throughout time. What's really interesting is if you, and it's unfortunate that the video didn't work, the movie didn't work because the movie was put together to sort of explain what's going on here. This is, we believe, the last time that we saw star B. So all of this time here, we were only seeing one star, we call it star A, while star B was covered the full time. When you look here, you see that each observing season, the whole system is becoming more and more obscured. And by the time you get here, basically both stars are covered, and you're really only seeing the reflected light of the stars moving in reflex motion about the center of mass. During this time, when it was fully occulted, we did have some observations taken at the sub-millimeter array on Mauna Kea, and we were looking for dust continuum emission. Unfortunately, the October 2010 observation had only a 4 sigma detection, and then when they looked again in 2011, they couldn't detect it at all. So we're not really sure if this was a real detection or not, but basically you don't see it in the millimeter. What you do see, however, is molecular line emission of carbon monoxide, and it turns out that line is spatially coincident with the filamentary H-alpha or molecular hydrogen that Tokunaga imaged. And so here's all the radio emission or the radio observations from the SMA. And when you look here, this is the position of KH-15D. This is really just the background of the nebula, and then this is associated with the KH-15D system. And when you focus in on that, you can see there is both a northern and a southern component in these molecular emission lines. Rachel Aronow, who was the author of this paper, took the Tokunaga image and very carefully aligned it with the molecular outflow. And you can see this, so this dark stuff here, that is from the Tokunaga H2 map. And then this is the rest of the molecular flow. What's interesting, however, is that it doesn't really exactly line up with KH15D. It's slightly off, and using the distance to KH15D, it's actually about 800 astronomical units away. So who knows? Maybe there's something else in the system that's driving that outflow. In 2011, I was on the way home from an observing run, and it was when the Wi-Fi on the airplanes was just starting, so I thought I would get on the internet, and there was an email from Bill, and it said, "Guess who's back?" And it was B. Star B had unexpectedly emerged, which was exciting, and so this was sort of where I just finished, and Star B had started to pop out. And so we immediately jumped on it and tried to see what Star B was all about. Holly Capello, who was also another master's student, got some infrared spectra and was able to tell us that Star B was a K1. So we have a K7 and a K1 in the system. Again, here's just another shot of how it's now coming back out the other side. And what was interesting about the work that Diana Windemuth and Bill had done is they started looking at, we'd always been looking at the colors, but it was really interesting to look at the colors from the other side. Between 2002 and 2009, we had always seen this sort of a bluing effect, and we interpreted that as the scattered light. And in fact, what we think now is that perhaps what we were really seeing was the scattered light of the hotter star, the K1 star, or maybe even that some of that light was actually coming through. So you'll see here in blue and purple, that's sort of the earlier star A, and that's what this line would represent. And then in the new scenario, where we're now seeing star B and star A is totally covered, you see it's going a little bit more red. So then here we have I minus J and I minus H. Magnitude on the y-axis, so when it's very faint, it gets very red. Yeah, so the colors actually redden quite a bit, even more than the photospheric colors of the stars, as one might expect. And so we've always sort of thought maybe there's a third body in the system, and we don't know if that's a planet, a brown dwarf, or something. I don't know if we'll ever know, but that is one thing that we like to consider. We have gotten ALMA observations, but it does not reveal a source at the position of KH15D, which is really a bummer. After seeing all these great ALMA images earlier today, it's sort of like, geez, I wish we could see something at KH15D, but we don't. The non-detection does, however, set an upper limit on the 2 millimeter flux density, and with certain assumptions, you can estimate that the total mass of the disk is 1.7 Jupiter masses, which is actually pretty high. So that's what we have so far. This is maybe a better picture if you haven't wrapped your mind around exactly this KH15D system. Back in the 1950s, into the 60s, and into 70s, both stars were visible, but it was star B that was being eclipsed, which is why the light curve, the whole light curve was higher, and the eclipses were occurring 180 degrees out of phase. And that's representing here number 1. Here's number 2, which is kind of, during the time when the eclipse was getting wider and wider and wider. That was because more and more of the orbit of star A was being occulted. Then here is position 3, where both of the stars were eclipsed. And now we are in the position star 4, where B is coming out, right? And based on the time between when we know it was visible to the whole thing was visible to basically today, you can calculate that we basically have this precession of about 6,500 years and a ring radius of about 4 astronomical units. And again, this is part of Rachel Arnaud's master's thesis at Wesleyan. Okay, so what's interesting today is the fact that not all eclipses are the same. They never have been. Some have been more regular than others. And what we're finding today is that there appear to be clumps of material that are, it's no longer a knife edge. Okay, so if you look at this plot, we have V, R, I, J, H, and K. This is over phase, right? So a 0.5 of phase is totally out. And this would be an ingress. This would be an egress, and this would be an ingress. The colors represent Julian dates. So each color is a different cycle of the orbit. And so what you see is that, you know, for some cycles, they match. But then in other cycles, you have these weird, they don't follow the same shape, right? So this is from 2013, 2012, when both stars were covered, or just star B was starting to come out. And then over here, this is a couple of years ago, we're here on egress. Again, you're seeing there's some evidence that not only that there's obscuring material, but there's also some information here in the sense that it shows up in V, but it doesn't show up in K. So that starts to tell you something about maybe the particles or what's doing the obscuration. Again, this is kind of the same information, but more. So this is looking only at star A from 2000 to 2007. This is only looking at star B. And so what you can do is you can kind of look across at the I magnitude here. And again, this is that position factor I told you about, going from above to below the circumbinary ring. And the big thing that we find is that the shape is quite different, and the color also is quite a bit redder than it used to be. Again, this is a color image here, different colors along the x-axis, phase on the left, Vmag here on the right. And again, this is just showing you that that each cycle is different and can give you different information about what you're looking at. And we used to always modeled the ingress as a straight edge, and this was taken from Sylvia and Agol from 2008, their model, and so. And this is also not perfect, right? But this is really bad. So basically what we're seeing is that in this new phase of the KH-15D system, it's can no longer be modeled as a straight edge, a knife edge cutting across. And the picture that we're sort of using now is one where we think of the back edge as being kind of clumpy. And not sort of this solid, hard edge that's cutting across. And so this is where we were last season, 2 seasons ago, 2018. And so I think there are just some open questions that we might want to consider. We really don't know if there's a planet that is maintaining that 5 astronomical unit edge of the ring. There are new models that we've talked about here as well that can form rings without shepherding planets. And Fang et al., while talking about the oxygen 1 lines being part of a disk, suggested that perhaps the outer part of the disk has been photoevaporized because there is a hot B3 star that's very like 37 arc seconds away in space on the sky. And I think it was just less than a parsec away or something like that. And also, there's still the open question, how is this jet being launched? Who's launching it? Where is it coming from? Conclusions, of course, we should keep watching this thing because last season's data has now started this return to mid-eclipse, right? Return at mid-eclipse. And what that tells you is that star A now is getting very close to the edge because as it moves up, its light is scattered forward. And again, here's more evidence of that clumpiness that's sort of maybe even on the size of a stellar diameter. So we're not sure what's going to happen, but this is what's happening. So we need more photometry. Turns out that the SMARTS consortium, if you're familiar with that, down at Cerro Tololo, is no longer functioning, and that's where we got all our great data from. So we're kind of scrambling. We have some capabilities of getting photometry, but more is always better. And anybody with infrared options would be awesome to talk with. And then we're working on getting some high resolution spectra with IGRINs, hopefully in May or in March. If we're lucky, we just put in that proposal. And please email me if you're interested in talking or having any information. I'd love to hear from you. Thanks.
Thank you very much. Questions?
Yeah, so this is, so there's star A. This is star B, the last time we saw it. Right there, okay? And now what you see is that star B gets close to the edge and the whole system gets brighter. That's sort of the return to maximum brightness. But as time goes on, star A spends less and less time above, which is why the eclipse got wide over time. And as it's going, you can still see a sinusoidal brightness. And now what we believe is happening is that whole edge is moving. So we're seeing the bottom side now. We're seeing B coming out the bottom.
I guess I just want to make a comment that I guess it's not super surprising that you didn't detect anything with ALMA. Because was there a reason why you chose band 5 for this?
I don't know. I was not part of that. Okay. Yeah.
So I would encourage you to go back and choose band 7. It's the most sensitive probably. If you're thinking it's a lower mass disk, band 7 would be better, or band 6, because yeah, the limits weren't like a Jupiter mass. Is that of dust or the whole disk? Of the whole disk. Yeah, I mean that's not. It's in other star-forming regions using the same approximation for disk mass. Mm-hmm. One Jupiter mass is on the high end. Yeah, so I would encourage you to go back and map it out. I think it would be really cool to see what this looks like with ALMA, and I think you will probably detect something. Yeah.
Further questions?
The question is the following. This is a young binary system surrounded by second binary disk. In such system, we know from observations and from simulations, there are fluxes of matter from second binary disk to companion. And the emission spectra which you observed are result of accretion process onto companion. But the question is, why you did not observe any times the intersection of line of sight by stream of such metal?
I don't have my H-alpha files here, but I believe there's one profile that I have of H-alpha that has actual shoulders on the profile. So you see a self-absorption over the double peak, and then very wide, broad, like 300 kilometers per second wide shoulders that we interpreted as inflow of a stream, possibly from the circumbinary ring to the stellar star A, basically. We would love to get the same kind of spectra for star B to see if we see that same structure so that maybe we could disentangle who's got the gas, right? Is it going to star A? Is it going to star B? Is it going to both of them? So that's something that we're looking at in the future.
The possible answer is the following. This stream of matter are optically seen.
Yeah, of course. Yeah, sure.
Any more questions? I have a very quick one. Do you know the K magnitude, roughly?
Off the top of my head, I want to say 14.
14.
Yeah,
Okay.
but I can check and make sure.
Okay.
It's that.
Thank you.
Yeah.
Okay, if no questions, then let's thank the speaker again.